Okay, now today I want to discuss differential graded modules of differential graded algebra, differential homological algebra. No, maybe a little bit. No, not very deeply, but okay. Differential homological algebra. So we have some R is commutative ring. It's our graded ring. We have A is differential graded algebra over R connected. So A is sum of AN, A0 is R. I have multiplication and differential, increases degree. Homological differential. It's R module and so on. And I consider M is differential graded module over A, which means that it's differential graded module over R. So it's also non-negatively degree, of course. Yes, non-negatively degree always. It's R modules. I have multiplication by element of A, and I have also differential on A, differential on M, increasing degree, and of course, and Leibniz rule here, Leibniz rule, Leibniz rule, and also here also it's true, Leibniz rule, graded Leibniz rule. Okay. So now again, I can define left A modules, right A modules. I want to discuss tensor product and Tor functors today. So now how to define, for example, tensor product? Now we know how to define. We discussed how to define a graded tensor product. No, so yes, it's generalization of graded picture. Yes, if we have differential size 0, then it's just graded modules of graded algebras. We discussed this. And so if I have two modules, I can define this thing as graded A module. We define this. It's a quotient. No, it's quotient. It's modular R, modular these things. Yes. It's graded ideal, so it's in fact it's graded module. It's graded R module, it's just R module because R is commutative. It's not A module, it's graded R module. No, and now I want to define its graded R module. No, and I want to define differential. No, by Leibniz rule. Differential defined by Leibniz rule, d of M tensor n. And you can check that this differential preserves this ideal, and so you obtain differential on this tensor product. So in fact, it's differential graded R module. No, and I want to define some. No, and also I have coordinals, co-coordinals. In fact, it's abelian category. I have short array sequences, and this tensor product is right exact, but it's not left exact, and I want to define derived function, Tor. And how to do this? Well, to define Tor, in general, how we do this? We consider projective resolutions, and then apply our functor and compute homologies, yes, or homologies. But problem here is that in this category of differential graded modules, or A modules, it's not enough projective objects, projective modules. Let's see this. Okay. No, in fact, the problem is just, for example, that free module is not projective in usual sense. For example, if I have no, for example, one-dimensional free module, just A itself, yes. And I have two differential graded modules. No, of course, no, map morphism between differential graded modules. It's morphism of A modules of graded and respects no differential computes with differential. Okay, it's map of graded differential modules. And it's epimorphism. I have some map here, or maybe where F. I want to define lift. Because it's maps of A modules, it's always no. It's defined. It's determined by image of unit. Yes. No, it's just some element here. Unit goes to f of unit, and I want to define f roof of unit. But what is d of unit in A? Why? It's because of Leibniz rule. Yes, because it's unit. I have a Leibniz rule, and it's in 0 degrees, so I obtain dA unit plus dA unit. So dA unit is equal to dA unit plus dA unit, and this is always 0. It is always 0. So yes, it's 0. And so because my f pre-source differential, d of f unit is always f of d unit is 0. So this element is cocycle because it's image of cocycle. And f roof of unit is also must be cocycle because it also must be no image of between of unit with respect to some no using some homomorphism. So it also must be cocycle. So I need to choose some element from M, some cocycle. Let me define by this as cocycles. Cocycles of M, which goes to my cocycle f of unit. And it's not always can be done because no, I know that my map is surjective, but here I need that it's surjective on cocycles. I need that the corresponding map on cocycles is also surjective. Then it's okay. I have unit that goes to something. I consider lift and I obtain lifting. But this is not always true in general. No, if you have a surjective map of differential modules, it's not always true that it's surjective on cycles. If it's not surjective on cycles, then there exists some cycle which is not lifted by cycle, and so there exists some map which does not have lifting. So if it's not true, if it is not epimorphism, then A has no lifting for some map. No, and if this exists, and so A is not projective in general. No, so we have problem, but we see the only problem. They're not surjectivity on cycles. So we see that our property to have lifting for any epimorphism is very strong. It's strong such that we have no such objects maybe. Or maybe only 0, for example. But we don't have enough modulus which projective with respect to any epimorphism in our usual sense. So we need to weak our notion of projectivity. It's equivalent to say that we need to restrict our we need to a little bit extend our notion of epimorphisms. Oh, sorry, we need to restrict our notion of epimorphisms because we have so much epimorphisms, so we don't have projective maps. We need to restrict our class of epimorphisms to obtain a little, maybe larger class of projective modules. No, so we say that epimorphism of differential modules is proper epimorphism if it's epimorphism on cycles also. Because it's differential map, it's always sends cycles to cycles. No, it's epimorphism on cycles. Then it's proper epimorphism. It's epimorphism and epimorphism on cycles. And so proper projective, it's such, P is such that if you have proper epimorphism and map, then you have lift. Proper projective. For example, from this we obtain that any free module is proper projective by this, because you only need lifting for cycles. If you have them, then you obtain it. So in fact, it's not true that it's okay, but in fact, no, it's also not true that any differential module has epimorphism from free module as differential module. Where it's that direct sum of differentials here, because differential, it's true for graded modules, but for differential you have differential, and differential is abstraction. No, of course you can find some, you can consider E alpha goes to M alpha, but maybe you have some relation between differentials of M alpha, but here your differential is diagonal, so it's not differential map. No, for example, I don't know. What D E alpha. For example, D A E alpha goes to no, sorry. What I want to say? Yes, no. It's okay. But maybe this surjection is not proper, what I want to say. To construct resolutions, I want that I want projective objects and the epimorphism of my class from which my projective model is projective. So in fact, my goal to construct the homological algebra, I want to prove that for any model there exists proper epimorphism from proper projective. No, this epimorphism may be not proper, because this map does not control cycles in general. Maybe it's not proper. So okay, if I construct this thing, then in fact I can construct resolutions, and for two resolutions I have comparison and homotopes, because if I have resolutions and this is proper things, if I have any other, I have this map and so on. I can then all my proofs works that resolution is unique up to homotopy, and so I can define, for example, derived functors. So I need to do this. I have my class of epimorphisms. I need to check that for any module there exists proper epimorphism from the proper projective module, which has lifting property with for this class of morphisms, for these epimorphisms. Okay. Now let's check this. First proposition. The main observation first. For example, let's consider a situation over not over A, but over R. Over R. Let's check the following simple observation. What if I have consider differential graded modules over R, not graded, not differential. Then I also have definition of proper epimorphism. I have it's just chain complexes over R, co-chain complexes over R. So I have a notion of epimorphism of co-chain complex, which epimorphism on cocycles is proper epimorphism. And let me say that if P is differential graded modules over R, it's co-chain complex. I say that it's splitting. No, it's of the manner what we did some time before. No, it's just of the form just of the form, or maybe C. Fitting means that in each degree I have Ci is just 2Ci minus 1 is just direct sum of Bi, or maybe it's cohomology, sorry. Bi cohomology and Bi plus 1, and differential goes, this Bi plus 1 goes identically to Bi plus 1, and this goes to 0. So, and this is just, no, this is cycles. So it's direct sum of cycles and boundaries. Boundaries goes to boundaries identically. Cycles is direct sum of the previous boundaries and homology. Okay, it's split in chain complex. It's direct sum of homology cochain complex with zero differential, and and direct sum of such chain complexes which has only one place of this form, something like this, something like this. Yes, it's a differential splitting complex. We checked that for any resolution, for any chain complex of modulus, we have resolution of such form, in fact. Yes? I think we checked this, that in fact, for any chain complex, okay, yes, and I say that this split complex is projective splitting if it's splitting and any of such modulus are projectives. No, it's equivalent to say that this map is projective because it's the direct summons. It's projective splitting, P is a splitting, plus Pi is projective R modulus, And we checked the important observation that for any chain complex, no, we have chain, here is cochain. I have resolutions of projective splitting modules. I have resolution where here is projection splitting modules, such that if I consider, no, it's exact sequence of chain complexes, and each this chain complex is projective and splitting. And if I consider homologies, I obtain projective resolution of cohomology. No, H is 0, H 1, so on. But some I. We checked this, in fact, in the beginning of the course. No, it's more or less doing inductively. It's generalization of that if I have short exact sequence, of modules, and I have two resolutions here, then I can construct resolutions in the middle as direct sum. It's the first lemma, and if I have this lemma, then each chain complex I can divide by these short exact sequences. I have boundaries, cycles, cohomologies, and I have cycles, Ci, and the next boundaries as isomorphism theorem. Yes, modular cycles is the modular kernel's image. Okay, and for these two terms, if I know this, I consider any projective resolution of H, consider any projective resolution of B, I obtain projective resolution of Z as direct sum, and then I have projective resolution of this, and projective resolution of this, of the following number. And then it's direct sum, and this is my claiming resolution. It's direct sum of three things, of B, Bi plus 1, and Hi. And differential goes in this form. No, it's more or less, it's not very hard. It's more or less obvious. Okay? It's more or less clear? Okay. Okay, and so this is our first main observation, that we have so for any, no, it's our zero observation because we did this before. For any chain complex, I have a projective splitting resolution. Projective split resolution. No, over R so far. Now the first observation that over R, projective splitting is proper projective. Over R, projective splitting is proper projective. Let's check this. No, in fact, no, I think it's maybe it's an exercise because what we need to check that if I have two cochain complexes, epimorphism, which is also epimorphism on cycles, and I have projective splitting cochain complex, I have map, then I have splitting. No, as I said before, my P is direct sum of homology with zero differential and direct sum of something like this. Two terms cochain complexes. So it's direct sum as chain complexes. So in fact, no, it's enough to check this for these chain complexes. For chain complexes with zero differential and for chain complexes of two-term chain complexes. Sorry, what? Yes. Identity. And this identity, such chain complexes. No, for this situation, it's more or less obvious. No, again, HP is just direct sum of HEP in each dimension with zero differential. So you need to check that if you have chain complex in one dimension, in only one dimension, consists of cocycles with zero differential. No, then it follows from the surjectivity on cycles, because if you have chain complex in one dimension, consists of cocycles, it goes to cocycles, and because it's projective module, R module, so you have surjection of modules and projective module, and you obtain map. Because it's projective R module, just projective R module, and it's surjection of R modules. So you obtain lifting. No, it's for one term submodules. For two term submodules, no, okay, no, you need to check this. You have these modules, you have this cochain complex identity. What you have? N in some dimension, I. You have N. No, in fact, yes, this is in dimension. This is in dimension I. This is in dimension I plus 1. You have some maps such that it commutes. No, it's easy exercise. Okay, for this cochain complex, I think it's not very hard. Again, using that it's projective modules and using that on cycles, it's epimorphism. It's an exercise. It's an exercise. Has to check that for two-term complex. If P is B in places I plus 1. Any such P is direct sum of such and one-dimensional. One-dimensional is just step. For this is two steps. No, it's more or less obvious. Okay, so it's important. We obtain we have example of proper projective modules over R. Okay, now let's consider over A. Now let's consider over A. The second observation is that it's always all. If I have that now let's V is a proper projective R module. No, differential graded module. R differential graded module. So cochain complex. So then for any such module, I can consider A graded over B over R. And this is now differential graded A module. Differential graded A module. No, with differential with the Leibniz rule and so on, okay? And it's A module via multiplication from the left by A, okay? If it's R module, it's A module. And this is its proper projective. We know that such modules are enough over R, and by tensoring with A, we obtain that these modules are projective over A. No, it's more or less from the following thing. It's just from, no, we need, no, we have M, N, A tensor V. We need such lift. No, it just follows from the following adjunction. What is home as differential graded A modules from A tensor R V to differential graded A module something M. What is it? It's the same thing as what? No, it's extension scalars, yes? It's differential graded extension scalars, but it works. It's just home F differential graded over R from V to M, where we forget A module structure M. So I need to consider this situation, but here, no, it's my previous observation. This, no, my property that it's proper, it does not depend on over each ring I consider this map. It's just epimorphism on cycles. Differential does not depend on A or R I consider this. It's just epimorphism on cycles. So I have splits, and so I obtain this thing. No, by formula is something like if it's S, this is S roof of AV, no, just A, S roof V. And you can check that this adjunctions, no, this isomorphism respects differentials and so on. You can check that this formula respects differentials. Okay. So what? So what we obtain? Let's consider. So I have some differential graded A module. I consider it as R module. So I obtain. Yes. Let me again over R. What we have over R? Let me check this again. Over R we know all because let me recall again. If I have cochain complex, I have cochain complex. If I have splitting projective resolution, then as I said before, if I apply cohomology, I obtain projective resolution of cohomology. But also, no, from definition, it also follows that, no, also it's true for cycles, for example. So on cycles, it's also no, it's not. No, yes, it's cycles. No, yes. So for example, on cycles, it's also projective resolution. Yes, and on boundaries and so on. No, now I want only one epimorphism. So if I have this epimorphism from projective splitting R module, then in fact this surjection is this epimorphism is proper. So in fact it's also epimorphism on cycles by construction over R, and on homologies and so on. Homologies, it's also surjections. Oh yes, I don't write degrees. So I know this over R. No, but now I can just tensor with A. I have this map from this. This map is epimorphism. No, of course it's epimorphism because I have map here just goes where to unit V. And this map is epimorphism, so this map is also epimorphism, okay? No, it's just more than this map. It's just, I don't just even consider images of V, I can multiply it by elements of A. No, it's just from V, it's also surjective of R. So it's surjective of A, тем более. Значит, on cycles. What is on cycles? No, on cycles it's the same thing. I have that ZM, ZAV, I have map. Here, no, what the, no, by this map, cycles also goes to cycles, because if V is cycle, this is a cycle, because unit is a cycle. So cycles is also goes here, and they have surjection here, so it's surjection on cycles. And on cohomology also, the same thing on cohomology. I don't say on cohomology, but in fact, if it's surjective on cycles, then it's no. If I say that it's exact, okay. So on cohomology, it's also surjective and exact and so on. Yes. Surjective, so this is surjective. So I obtain epimorphism, which is epimorphism on cycles, and additionally on homologies. Okay. So it's proper epimorphism from proper projective map, and it's enough. It's my start of resolutions of homological algebra. So I have projective resolutions. In fact, this is exactly the replacement of free modules. It's our free modules. You can check that by projective, by proper projectiveness, you can check that any proper projective module is direct summand of such of this module. No, because if you have proper projective module, you can consider proper epimorphism from such module, consider identity, and so obtain splitting. Okay, so this is our replacement of free modules. It's not free this is free with respect to differentials. It's tensor with some cochain complex over R, projective cochain complex over R. It's our yes. If you want, you can consider this chain complex over R is free. So it's yes. Any projective resolution, any projective proper projective module is direct summand of such modules. You can use these modules for resolutions, and so you obtain. Okay, let's consider how to construct resolution. Let's check maybe. So I have M. I have proper epimorphism from something like this, for example. I have kernel, and I have proper epimorphism to kernel. Now let's check that. I want to check that, in fact, and so I obtain some exact sequence. I want to obtain that this exact sequence is exact on cycles and exact on homologies also. No, it's exact. Why it's exact on cocycles? No, it's more or less because of proper surjectivity. So for example, what I want to check that exactness in this place. For example, I know exactness in this place by definition. As I said before, it's surjectivity on cycles. Why it's exactness on this place? No, if I consider cocycles, I have cocycles goes to cocycles. I know that surjectively. And what the if I have some element which is cocycle and goes to 0, what does it mean? No, it's independent properties to be cocycle and goes to 0. So it's just cocycles of kernel. It's kernel and cocycle. This is submodule, differential submodule. So this is kernel is just this map. It's just kernel. And I know that it surjectively goes from cycles here. So I obtain exactness on cycles here. Why it's exact on homologies? Something like this. Okay, again I have. It's clear why it's exact on cycles. Okay, it's because I claim that this kernel is just cocycles of kernel. No, because what is kernel? It's cocycles. and kernel. Which it goes to 0 and cocycle. It's independent properties. To be cocycle and it goes to 0. So it goes to 0 and cocycle. It's just cocycles of kernel. It's commutativity of these two properties. Cycles, cocycles of kernel is kernel of cocycles. More or less this. Okay, but on homology, what I also have this thing. What I have on homology? But on homology, I have this short exact sequence of cochain complexes, for example. So I obtain long exact sequence on homology. So I have HM, H, HK, but I know that this map is epimorphism on cocycles. But if map is epimorphism on cocycles, it's epimorphism on cohomology, because any cohomology class represented by some cocycle, I can consider preimage, cocycle preimage, and this is, no, it has a cohomology class which goes to my class. So surjectivity on cocycles implies surjectivity on cohomologies, okay? So this map is surjective, and so my long exact sequence is short exact sequence. And again, from this, I obtain that here is not very obvious, but it follows from long exact sequence on cohomology, that cohomology of my kernel is kernel of my cohomology. This cohomology of my kernel is just kernel on cohomology, and so, and again, I know by the same argument, it's surjective on cycle, so it's surjective from cohomology of A tensor B1. So I obtain that this image is exactly this image, and this is exactness on this place. Okay? Okay? Вот. No, so I obtain properly, I obtain a resolution which is exact on cocycles and exact on cohomologies. Properly exact resolution by properly projective modules. So I can do homological. So now you can easily check by the same argument that this resolution is unique up to homotopy, it's natural up to homotopy. And so you can obtain derived functors. For example, you can obtain Tor. But no, okay, how to define? Let's. Okay. Yes, and maybe the final. I said that I obtain a resolution on homologies. It's important. It's exact sequence. But now let me one another observation. What is this cohomology? No, it's easy observation that if C is splitting and D any cochain complex, then what is cohomology of C tensor? No, maybe splitting and no, what? Yes, what this tensor product? No, it was an exercise sometimes before. No, it's just no. Why? No, it's no, C, as I said before, it's direct sum of homology of C with zero differential and some direct sum of this is B to B identity. This thing is not just acyclic. No, it's of course acyclic. Yes, it's acyclic. Yes, because it's identity. It's no homology. But it's not just it's just contractible. It's homotopy equivalent to 0. From this, no, it's easy to obtain homotopy equivalence with 0. So this is homotopy equivalent to 0. And so this thing is cohomology of cohomology C with 0 differential tensor D plus something homotopy to 0 tensor D. No, if you consider something homotopy to 0 and then tensor BD, it's also homotopy to 0. So this direct sum is homotopy to 0. It does not. So our homology doesn't depend on this. And so you obtain homology of some cochain complex with 0 differential and some cochain complex. No, this tensor product you can just move this out and obtain this HC tensor homology of D. So if C is splitting, then no, it's Q-not formula, but it was when we proved general Q-not formula, it was the lemma that because we proved general Q-not formula from this lemma that for splitting, because no, we used resolution, splitting resolution, and we need to know that for splitting cochain complex it's all okay. No, it's all okay for splitting chain complex. The Q-not formula works. So So in fact, this thing is splitting. Here we consider over R. So in fact, this thing is HA tensor HV. And another easy observation that, in fact, if M is differential graded module, then its cohomology, it's just graded module over cohomology. It's graded homology module. No, it's because I have map. I have map H A tensor HM. I always have a natural map from to homology of tensor product. No, tensor product of cocycles is tensor product. Tensor product of cocycles is cocycle. No, we know that this map is not surjective in general, but it exists. No, and then I have a multiplication map. So this gives me a HA module structure. Yes, this is kind of external product, or tensor product. Tensor product of cocycles is cocycle, and then this is map. So this is a module of a homology. No, and this is module structure. It's so-called extended modules of the same form. You have some module over R, and then you have HA module structure from this, just from this tensor factor. So, and again, and the final observation, we know that, as I said before, these modules are projective R modules. It's projective R modules. It's projective resolution of homology. So this is projective R module, and this is HA. It's a ring. And we know that if I have projective R module and I consider tensor product with some other ring S, this is projective S module. This is projective S module. So this is projective HA module. This is extension of scalars of projective R module. This is projective R module. This is our new ring, and this is extension of scalar. So this is projective R module. So this is projective resolution of my homology as HA modules, of graded HA modules. It's graded resolution. It's projective HA resolution. So I obtain resolution, which is resolution on cycles and projective resolution homology. Oh, and of course, projective resolution as modules. It's proper projective resolution of modules. Okay. No, that's all. That's our construction. Now, about differential graded Tor. So, okay, let N our differential graded A module. Now consider some proper projective resolution, which we constructed second before, resolution of F of N. Now let me write down this like something like this. I have here maybe I have N and 0 and 1 and 2 so on. It's my differential graded A module, differential, and I consider resolutions. I have P. Yes, I consider something like N P minus 1, P minus 2. It was, no, 0. It was negatively graded, not to be cohomologically graded, to be with increasing differentials. And has differential. So I have minus 1, 0, 0, 0, 1, 0, 2, and so on. Then minus 1, 0, minus 1, 1, minus 1, 2, and so on. What? This is the picture.
So may I ask about...
Just 1 second. What?
May I ask about the previous subject? We had these modules A tensor E over R, and
yes,
they are not free A modules since the differential is not diagonal.
No, yes, because our differential is through Leibniz rule in general, yes. No, yes, because I have Yes, no, for example, I have some differential on V. The free model it's kind of free model is what direct sum of A. It's just A tensor without differential here, And here I have some differential on V, so it's some differential free model. Yes, this is diagonal. If I have no difference here, it's some differential on V and some differential on A. No, it's different things. Yes, in general. No, for example, yes. No, this is difference between this. For example, it's identity, or this is 0. What if I tensor with A? Here I obtain A plus A is free. Here I obtain is V. It's A tensor V. And you can check that this is different differentials here. Okay, this is our proper projective resolution of my module N. No, I want to tensor it with M and obtain something like Tor. Yes, I have. Yes, I have. This is my augmentation. It's augmentation. This is my differential delta. It's my resolution differential. No, and my vertical differential is differentials of my differential graded module structure is D. It's capital D, dn, dp, and so on. Okay, so no, here I have B complex. Without n, I have B complex P. So consider this total complex of this B complex. With K is just direct sum of P M n m plus n is K. Note that m is negative and n is positive. So in fact, K is integer. It's not negative or positive. It's maybe negative and positive. It's not a bounded chain complex in general. No, it's chain complex of this diagonal. And this diagonal can be negative and maybe positive because you have some parts of the diagonal on positive degrees and negative degrees. This is diagonals. M plus n. Or maybe, sorry, not these diagonals. Yes. Yes, M. Yes, what exactly this diagonal, because it's -1, it's M, it's my number. This is exactly, this is M, this is M. Yes, this is my diagonals. M is negative, N is positive. Sums are arbitrary. And I have differential. Sum of differentials. В общем, delta maybe with some sign, something like m d. To be squared 0, because they commutes in fact. So to be so then this squared 0. Okay. It's z graded cochain complex. What total complex is z graded cochain complex. No, in fact, it's more or less easy exercise that the total complex is differential graded. No, it's differential graded, but it's a module. It's differential graded, but you have a multiplication here, because you have a multiplication on each part, and in fact, no, it also works. It's just direct sum. And you have Leibniz rule. Okay, it also works. Differential graded a module. No, and so yes. Yes. Definition. Differential graded Tor over my differential graded algebra between M and N. M is some other differential graded module. No, it's just homology of M tensor with over A with this total resolution of proper projective resolution of N. No, so yes, this is definition. Now you can check properties that what it's written here, properties which I'm not going to check because it's not very interesting, but it's not very hard. No, it's more or less properties are the same as for the usual Tor. The first is does not depend on proper resolution, for example. Does not depend, so it's functor, it's correctly defined functor, does not depend on the resolution. You can resolve, for example, left module with projective resolution, then tensor with n, you obtain the same thing. If your differentials, all your differentials are 0, so you have graded modules of a graded ring, you obtain overgraded algebra, you obtain the previous our usual Tor, no, our usual big graded Tor. Yes, and here it's big grading thing, so it's homological degree, but also the thing is graded, so in fact you have internal grading in fact. So in fact it's big grading thing, and if your differentials are 0, this is our previous big graded Tor for graded algebra, for graded models over graded ring. If you have no differentials here, no, it's just projective resolutions in each degree, you have just direct sum, no, it's the same thing. Yes, and if you consider 0 homology is just tensor product, and all higher Tors are derived functors, so they extend tensor product to long tensor sequence with short tensor sequence. So Tor 0 is tensor product, and higher are left derived, which means that they extend your tensor product to long tensor sequences for each short tensor sequences of modules. Okay, and on the next seminar, I will describe what does it mean in topology, where in topology this differential graded Tor arise. No, it's arise when you need to compute something like homology of, for example, loops and something like this. I give some examples on the next seminar. Now let me say about how to compute this. We have a spectral sequence which compute this differential graded Tor through usual Tor of homology over homology. It's a Limberg-Moore spectral sequence. Yes, what is its definition? Okay. No, it's just our usual spectral sequence of B complex because we have B complex in general. If I tensor it with n, it also will be B complex, and so its homology can be computed by spectral sequence. No, it's our situation in fact. So consider what we have total B complex, not total complex. Yes, it's complex, cochain complex, total complex. It can be filtered by something like this. It's как это? Decreasing filtration. Yes, decreasing filtration on the cochain complex, where it's just minus n is it's just this part, right part, greater than minus n. Yes, here was m, n here. By horizontal coordinate, it's true. By horizontal coordinate, yes, it's minus n. Let me clear this. It's filtration by horizontal coordinate. Okay. Because it's minus n, it looks like increasing filtration, but it's decreasing filtration because it's negative part. Okay, it's minus 2. It's bigger than minus 1, but minus 2 less than minus 1. So in fact, it's increasing filtration. If your number increase, your filtration decreases. Okay, it's decreasing filtration. Okay, no, so it goes from minus infinity to 0 decreasingly. F1 is 0 because I don't have, no, yes, I forget this part, so this is 0. I have only this 0, think it's my 0 filtration, and 0 is my F1 filtration. No, okay, it's a submodule. It's also, no, because my A multiplication works vertically, acts vertically in each pi. Okay, no, so I can consider, if I consider my tensor product, I obtain filtration of this tensor product by, and this filtration, oh yes, it's a submodule, so I obtain filtration by tensor products. And so I have complex with filtration, and so to compute homology, I want to, no, I have a special sequence of filtered cochain complex with decreasing filtration. I have cohomology type spectral sequence of homological type. First page -1 something is homology of quotients. Yes, maybe I need some place of quotients. What is it? No, it's M tensor on quotient, but what is quotient? No, quotient is just one column, yes? So it's homology of M tensor A. One column is exactly P minus 1. Minus 1 here. P minus n, sorry, minus n. And what is it? Now again, if you consider what is this cochain complex? By construction, not by construction, but maybe it's not arbitrary proper. No, it's not important because, but if we consider not proper projective resolution, as I said before, Tor does not depend on resolution. If we not consider proper arbitrary proper projective resolution by resolution by our construction, by extended proper projective, of the form of these things, okay, something like this, where Vi is splitting. So in fact, this thing is kind of splitting of this form. So in fact, I have if P minus n is A tensor R V minus n, where it's V minus n is R splitting, then this thing, if I tensor over A over with A, then this thing is the same thing as M over R V minus n, yes? A eliminated. This is cochain complex over R, this cochain complex is splitting, and as I said before, homology is that tensor product of homologies. Because it's splitting cochain complex. And again, I can add HA factor. Or maybe not in this place, in this place, because this is HA module, and this is, as I said before, this is just H of my resolution. So this is extension of HA modules. No, this is tensor product of HA modules, right and left. No, so and as I said before, this is projective resolution of my homologies by projective modules. This module is, this thing is projective. No, sorry, it's not projective. It's yes, it's projective HA module, and this is resolution. This is projective resolution of Hn. Yes. No, as I said before, This is extension. This is extension, as I said before. This is extension of projective R module. So this is projective module, and this is resolution. So because I know that my proper projective resolution is is exact on homologies also. So this is resolution of homologies. Yes. Okay. And so what I obtain? I obtain resolution of my homology tensor with some module. So if I compute homologies, I obtain a usual Tor. So because this is projective resolution of homologies as HA modules, my second page, if I compute the next homologies, is just usual Tor, n Tor, graded Tor because it's graded things. So now over HA between HM and HN. So now maybe I need to write down it here. So this is the end. So I obtain Eilenberg-Moore spectral sequence. Eilenberg-Moore spectral sequence is spectral sequence which starts from the second page of this form, HA, it's graded between HM, HN, and the target of this spectral space is differential graded Tor. Here is not obvious why this spectral sequence converge, and in fact, no, it's some issues here because it's exactly because my filtration is not finite, it's not locally finite because my diagonals in fact are infinite. My diagonals are infinite. So when your diagonals are infinite, your spectral sequence maybe does not converge. It's not automatically. But no, it tries to converge to something. It tries to converge to this. Its target. It's the goal. But maybe not converge, but it's the goal of the spectral sequence. When it converges, for example, when we know that it's converged. It converged when diagonals, in fact, on some page are finite. If you know that, for example, on the second page, your diagonals are finite, then filtration is finite, and so it's converged, okay? No, when I say that it's not converged, I don't know, you have some filtration homology. I don't know if this filtration is hosted, complete, as I don't know this. But if this filtration is finite, it's all okay, yes? So if this, yes, maybe this spectral sequence of the second quadrant on this place. It's minus n, it's n of second quadrant, and your diagonals in general are infinite, and so maybe it's not converge. When these diagonals are finite, then it converges. Way we can guarantee this. No, it's easy observation. For example, no. At this moment, I can't say when we can guarantee this. I say this with bar resolution. Okay, this is the end of the story, local end of the story. We construct some spectral sequence which starts with something usual and tries to converge to something unusual, differential graded Tor. This thing has a lot of applications in algebra, in geometry, and in topology, and I maybe say something about this about application topology on the next seminar. But now we need the next step. This is more or less all what I want to say about differential graded homological algebra. It's definition of Tor and definition of this Eilenberg-Moore spectral sequence. Maybe it's yes. No, this works. But for any modes, for any R commutative ring over which our A is, it works. It works always. It's okay. Now, how time I was? How time I was? Yes, sometimes. No, yes. Now, yes. Yes, convergence is not obvious. Now we need some about bar resolutions. Ну, maybe начнем только. what resolutions we have before? No, we have minimum for graded case. We have minimal resolutions. In commutative and for regular sequence, we have Koszul resolution, which was generalized. It was important that over characteristic zero, it was generalized for Koszul quadratic algebras. Also Koszul resolutions. Characteristic zero is important because, as I said before, no, it's Casimir. It's normalized Koszul differential, so you need something like characteristic zero. And as I said before, polynomial and exterior algebras are quadratic dual, so they Koszul at the same time. But no, so and this means that this construction says that Koszul resolution for exterior algebra is polynomial algebra, and it's only true for characteristic zero. As I said before, for positive characteristic, it's not polynomial. It's kind of divided powers, something like this. Not polynomial. But okay, in characteristic zero, it's something like this. Now, bar resolution is general resolution for arbitrary associative algebra. No, but maybe over a field, but maybe in some assumptions, but not very mild enough. Okay, no, so let's start. No, I don't know from just associative algebra. Okay, A is associative algebra. No, because we have a variant with grading and a variant with differential and grading. Now without grading and without differential, maybe. Associated algebra, maybe no associative ring. No, algebra over some R. Some commutative ring. What is bar resolution? Ну, maybe вот самое простое дать определение или самое сложное? Какое лучше? Do you know what the bar resolution is? Что? Okay, now I define this. One second, где тут простое было определение? Yes. No, of course. Yes, associative algebra over R, with unit, of course, associative with unit. So it's important here. Okay, let's start. No, by definition, something like this. We can consider something like this. A tensor tensor over R. I did not write this. It's d bar. That's d bar differential. How it works? Here it's just multiplication. What is on the higher terms? It's just something like this. On n term, maybe from 0. It's just some formula. And you can check that this is differential, so on. But in fact, no, this is just formula. You can say why this formula, and you need to check that this is, for example, squared zero. No, it's not very hard. It's more or less the same thing as simplicial differential. But simplicial identity is associativity of your algebra. It's important. D bar squared follows from associativity. It's important. But in fact, you have some a little bit cheating reformulation of this definition where it's more or less obvious. It's easy definition. Let me reformulate. What is this, in fact? I just want to consider what I have associative algebra A. I can consider yes, and in D bar, sometimes these tensors they denoted by it's not important. This polynomial algebra is also associative algebra. maybe, yes, maybe modulo squared 0. Вот так. Yes, k and epsilon and squared 0. It's associative algebra. The first one. If you have two associative algebras, then you have their free product. What is free product of associative algebra? No, it's more or less the same thing as free product of groups. It's just linear combinations of words in any order. It's free, so they're not commutative. It's not commutative algebra in general. And now I want to consider this. Yes. Сейчас, one second. Может быть, надеюсь, я не обманываю сейчас. Это будет совсем неловко. Yes. Maybe let me just denote it by epsilon. Epsilon is always meant that squared 0. Okay, epsilon is just dual number. It's always squared 0. So I will denote it by this. It's not polynomial. It's with this thing. So I will not write down what is this. Only with one relation. It's words, but here I have unit and epsilon, and unit is unit. So if in your words you have unit, then you can glue together, okay? Elements. So in fact, in these algebras, what's the element of the it's words? It's words of this form: a0 epsilon, a1 epsilon, and so on, okay? It's only one possible. Maybe epsilon here, but then I can say that it's unit here, so it's this the same situation, okay? I can assume that it starts and finished by n, by elements of a, maybe unit. And another observation: if you have associative algebra, if you have some two associative algebras, and if you have two associative algebras with differential, and differentials two differentials satisfy Leibniz rules, and you want to define differential on free product, what do you need to define? It's defined uniquely by Leibniz rule, because in each algebra, differential is unique because it's determined by differential on generators. On generators, you know what does it mean, and you does not have some contradictions. And so I can define differentials here. Differentials here. Here I have no differential so far. Here I can define differential something like d epsilon. Дай бог памяти. Unit. Unit, yes. D unit is 0, so it's the squared 0. Да. Вот. Here d is 0. And then what's the differential here? This is the same formula. If you denote epsilon by tensor, you obtain the same formula. It's just Leibniz rule for epsilon, where you epsilon, you have here g from 0 to n. So the first one you have d. Just 1 second. Yes, of course. The first a0 is 0, d of a0 is 0. So I have d of my ai is always 0. So I have nothing. Then I have d epsilon is unit. And so I have, yes, and my Leibniz rule, in fact, it's, yes, I need gradings here. Here I have no gradings. It's all in degree 0. And here I have grading to something, here is 0 and something like -1, yes? What? So in fact, it's graded algebra. It's graded by number of epsilons. It's number of tensors. It's the same gradings, okay? And so my differential is, it's a0, then differential of epsilon, it's unit. And if I replace d and epsilon, I obtain sign. The first I have no sign, and I obtain this thing. Then I obtain sign. It's -1. And the next time. And so on. I obtain this formula, okay? No, and it's obvious because it was differential and it's satisfied Leibniz rule that it's squared 0 because it's differential on free product of Leibniz. Because it's squared 0 on, if you have differential and it's satisfied Leibniz rule, if it's squared 0 on generators, then it's squared 0. And it's obviously squared 0 on generators because it's 0 and it's squared 0. So it's obvious. No, it's the same thing, okay? This is graded algebra and this grading is 0 epsilon, 1 epsilon, and so on. No, epsilon is standard sign. No, in this theory, it's always denoted by bar. So it's bar resolution. It's bar, no, it's some, как будет, разделительный знак, ну вот, как это, разделительный. Divided sign, I don't know. Some divided sign between elements of your algebra. Here you have no gradient on A and no differential. But now, from this definition, it's more or less obvious how to, maybe you have gradient on A. No, then you have gradient on A. Maybe you have differential on A, then you have differential on this thing, and you obtain differential graded bar construction. You have some formulas. Formula may be a little bit less obvious, but no, you have just some signs here, some additional signs which with degrees of A0 and differential. Oh, yes, maybe.
Bars appear.
Huh?
Bars appear same products.
No, yes. Maybe I say this. What was your question?
I mean, we have notation A bar is -1 to the power degree of A plus 1 multiplied by A, and in the general formula, if A.
No, general. Yes, no. General formula. I will say it's no. Yes. I will say it's more accurately. This is just associative. Yes. Now maybe no. Yes. Let's say about gradient, for example. Yes. Well, yes. This is the. We only have third definition, but maybe. Maybe not. Maybe let me just check one thing. It's unreduced bar resolution. We have wide resolution. What's resolution? No, maybe okay. Yes, wide resolution. It's just complex now. It's d squared is 0. What from this observation we obtain that d squared is 0. Okay. No, for example, it's 0 on generators and so on. Okay. Or you can check it directly from the formula. So we obtain some chain complex. Okay. More or less, it's chain complex. No, for example, again from this formula, because it's a Leibniz rule in 0 on D, if you have some algebra and you obtain some elements which are 0, which differential is linear with respect to multiplication on by cycles. I want to say that from this follows that AX is A dx. So this differential is A linear, in fact. Yes. On the things you have this over R, but you have, for example, from the left A module structure. For example, by multiplication from the left, and this differential is A left A module maps. Also, you have right A modules from the right, and this is also right A modules maps. In fact, it's AAB modules. It's AAB modules, and differential is AAB module maps. In fact, no, it follows from this and from this. It's from Leibniz rule. And that so in fact this is a chain complex of AAB modules. In fact, it's exact. Why it's exact? Why it's exact? Так, надо уже закругляться. Ну ладно, значит. Why it's exact? No, in fact, it's contractible. And again, contractibility much more obvious in the second interpretation. No, it's just because it's in second interpretation is more or less obvious because no, you have that your bar construction. It's not this bar complex. It's bar complex. Yes, bar. It's bar. It is complex. It's just A free product with K epsilon. It's important with the differential. Yes, yes. And no, why this chain complex. Why this chain complex is contractible? No, because it's algebra. It's algebra, associative algebra. It has unit. No, and unit is co-boundary. It's d of epsilon. If you have algebra and Leibniz rule differential and unit is co-boundary, then any homological class is co-boundary because it's unit on something. No, any cycle is co-boundary because any cycle is a cycle on boundary on unit. No, any cycle, any x such that the x is 0. No, x is x unit. A unit is boundary, so it's x d epsilon. So it's d x epsilon. So we obtain any cycle is boundary. So in fact, no, at least it's acyclic. Of course, it's contractible. It's proves that it's acyclic, but in fact, no, this is homotopy. It's multiplication by epsilon. You can consider multiplication by epsilon from right or from the left. And this formula says you that in general, even if x is not a cycle, then in general Leibniz rule gives you that dx epsilon is dx epsilon plus x d epsilon. What там? Some sign, yes. Degree of x, maybe x is from some epsilons, here is also some degree. No, this means that this is unit. No, this means that this is up to sign multiplication by epsilon is homotopy between identity and 0. So some signs multiplication by epsilon up to sign s, and then sd plus ds is identity plus 0. So it's homotopy between identity and 0. Okay. So it's contractible. It's contractible. So any algebra in which x is boundary, then the multiplication on this boundary it's contraction. Okay. So it's contractible Cauchy complex. So it's exact. Contractible. So it's resolution. It's bar resolution. Значит, последние слова. Значит, вот, значит, exact. No, and what is reduced? Reduced bar construction. It's when we consider something like. No, again, let's at first in the second interpretation. But it cannot be happened. Sorry, it's not true. Because d epsilon squared it's 2 epsilon d epsilon. D epsilon is unit, and this is not 0. It's real polynomial. Sorry, forget this. It's polynomial, but it's all correct because in fact, yes. As I said before, maybe if you have some epsilons here, but then I can assume that it's unit between them, and so maybe unit between them, and this is correct. And then any word is of this form, and so on. Okay, and then all correct. Sorry. No, this cannot be happened if epsilon squared is 0, if it's not in characteristic 2. So, but all other correct. So we have this just polynomial algebra. And that's just words, that's differential, and so on. And multiplication by epsilon, yes, it's homotopy, and so on. Sorry, it's just polynomials. My fault, sorry. And now I want to quotient by squared. Yes, what now? It was a reduced thing. Now I can consider ideal epsilon squared. And this ideal is this ideal. Сейчас, что я хочу сказать? Sorry, no. Нет, it's true, but as I said, what I said before, it's not true because what's the differential of epsilon squared? Differential epsilon is not 2 epsilon. Sorry, it's 0, because no, because epsilon of degree 1. So so it's not commutative, and it's not graded commutative. But no, it's d epsilon epsilon minus epsilon d epsilon. So, and this is unit, this is 0, sorry. So in fact, it's not a contradiction. No, this is because this works. Sorry, so it's only works. So we can assume this, but I a little bit fastened. Sorry, here we did not assume this. Yes, but we can assume because this is 0, and no, and it follows that in fact for any x, I have no, because it's 0, it's linear with respect to them, and I obtain this thing, and this means that the ideal is no, preserved by differential. It's differential ideal. So I can consider my algebra modulo epsilon squared. No, this is the same thing as this thing. It's the same thing. Yes. And what does it mean? This means that if I have some word, what if I have this is unit in some place in the middle, not the first and not the last. If this is unit, then I obtain squared, and this is 0. So, what does it mean? Okay, now again, consider the following short exit sequence. I have my algebra. I have my ideal. Is subcochain subcomplex and quotient. It's a short sequence of cochain complexes, and my homotopy, my contraction, no, preserves this ideal because no, it's multiplication by epsilon. If I in this ideal, then I again in this ideal after multiplication by epsilon. So in fact, this contraction contracts this and contracts this. This also works for this. So this is also contractible. What I want to say. This is contractible. This is contractible. No, this is contractible by our contraction, but my homotopy no correctly defined on this ideal also because it's multiplication by epsilon. So this is also contractible. And so this is also contractible because it's not contractible, it's acyclic. It's acyclic because of long X sequence in homology. If it's 0, then it's also so it's acyclic. Acyclic. No, and this called reduced bar resolution. What is in the tensor notation? Reduced bar resolution. In tensor or bar notation, no, what does it mean? This means, as I said before, that no, for example, what here, what is here in bar notation? This means that I need some epsilon squared somewhere in the middle. This means that I need some unit. So this thing in bar notation, that in nth term I have a, but such that in some I have a, but I need some unit in some place. It's because I need epsilon squared somewhere. Okay? It's the same thing. It's a submodule in this all module of such things where I have some unit in some place. It's also contractible because my homotopy on this preserves these things. And so, no, a quotient, what is quotient? No, it works, for example, in the following situation, if you have so-called augmentation. If you have algebra and you have, no, okay, epsilon, sorry, no, not epsilon, I don't know. Augmentation, to k, yes? You have inclusion of unit, and if the inclusion of unit is have projection, is inclusion of direct summand. If I don't remember over commutative ring, yes, if your unit is a direct summand, no, then this is just quotient by this direct summand. If I consider this quotient by A bar, then in fact this quotient, if I quote by any tensors where I have unit in some middle term, I obtain that in fact this thing in tensor product is just A and then A bar in middle terms, A bar, A bar, A bar, A bar, A bar. I just quotes by any unit in middle terms. If I obtain any unit, it's 0. It's the same thing. So this is reduced bar resolution. And formula for differentials is the same formula. No, from this observation, this observation implies that it's correctly defined quotient complex, and this also acyclic, and also AB module. So yes, what with d bar? It's bar reduced bar resolution. Okay. It's also a resolution of AB module. It's this thing. Okay? No, okay, I then think it's time to stop, maybe, yes.